At no point in your rambling, incoherent response were you even close to anything that could be considered a rational thought. Everyone in this room is now dumber for having listened to it.
You lose! Good day, sir!
Hi, welcome to CheMistakes. Here we go through actual student responses to chemistry questions and try and look at how we can improve them, communicate them better, and fix any misunderstandings that are there from the answer itself. Here we have a specific heat capacity problem. We're given the specific heat capacity of gold, right here. We're asked how much energy does it take to heat 44 grams of the gold, so the temperature changes by this amount. Okay, so student response. They started with, I call it Q equals MCAT here, but Q equals MC delta T. They plugged in the 0.130, the 44, it's specific heat capacity they don't know, and the 88, they solved for C and got this as the result. So this is not correct, but the underlying features here is that the student does not have a complete understanding of what specific heat capacity is, which is very understandable because specific heat capacity is a challenging topic to have a conceptual understanding of. And so one of the shortcuts to this is a mathematical understanding. So let's start with that, but then eventually build in the conceptual as well. So the 0.130 with the units of joules per gram per degree Celsius. Most students are relatively new to the units of joules, and so the combination of all three units into one thing is very confusing for a student. So that's showing up here that the student is not sure what to put in, and they actually confuse Q with C when they plug in the amounts here. So let's talk about what this means in a numerical perspective or a mathematical perspective. This is the number of joules required to heat up 1 gram by 1 degree. So when you're seeing the units here, we can think of this as in a per sense, joules per gram per degree Celsius. And if that's never been explicitly stated to you, when you say the word per, that implies a per one. So this is the amount of joules necessary to heat up 1 gram of gold by 1 degree. Now if we look at this problem, we don't have 1 gram, we have 44 grams. So we'll need 44 times this amount to heat up each of this set of 44 grams by 1 degree. And we don't heat them up by 1 degree, we heat them up by 88 degrees. So we're going to need 88 times that amount to figure out how much total energy is required. So if we can understand the units a little better, that might allow us to then figure out how to plug things into our equation a little better. So really this here is our specific heat capacity. What we should be doing is plugging the 0.130 in for there. So we are starting with Q is equal to MCAT, or MC delta T. But Q is our unknown. We're looking for what's the amount of joules, what's the amount of energy. Now Q is heat, which does not match this term, but the amount of energy transferred is equivalent to the amount of heat being transferred. That's what that is. And so if we plug in now, we have 44 grams times our 0.130 times our 88 degrees Celsius. Now I'm plugging that without units so we can see the numerical calculation, but let's plug that in with units as well. So 44 grams, it's 0.130 joules for each gram. So 44 grams will be 44 times that amount of joules. And then we change our temperature by 88 degrees Celsius. Every 1 degree Celsius requires this many joules. So we have 44 times as much, and we have 88 times as much. So when we total that out, we can come up with our answer. So that comes out to be 503.4. And let's check our sig figs here. We have 3 sig figs, 2 sig figs, 2 sig figs. So we would round that to 500. We run into a little bit of challenge there. So we could change this to 5.0 times 10 to the 2 joules. Now, that's a mathematical approach, an analytical approach to what specific heat capacity is. But now let's look at it from a different perspective. Now let's look at what is specific heat capacity. So what is this constant here? And for that, we're going to go back to heating curves. So if you have drawn a heating curve, we're looking at a perspective of temperature. Now sometimes they'll write time here, but really they mean the amount of energy added. So heat. And we'll see a curve that looks something like this, where this point right here is your boiling point. So let's assume we're talking about water for a second, 100 degrees. And this is your melting point or freezing point. So in the heating curve, when we're changing temperature, there's a particular slope here. There's a relationship between how much energy is supplied and how the temperature changes. Now, it helps if we kind of flip this. So I'm going to take this little segment here, from here to here, And I want to flip the axes so I end up with Q versus temperature. Okay, now when I do that, that's going to obviously invert the slope. But let's take a look at two substances here, one like this and one like this. Okay, we'll call this substance A and substance B. So the implication here is that when I go through and I change the temperature so much, so I go from this point to this point, I change the temperature by 12 degrees, let's say, that the amount of energy necessary to heat B up to 12 degrees more was this much. But the amount of energy needed to heat A up was this much. So A required more energy to change the temperature by the same amount, which means that I'm putting in the same amount of energy, but the motion of A is changing by a greater factor in terms of kinetic energy than B is. So the way we would state that is that A has a larger heat capacity. Thinking of the ability to store energy. So that means that A, when you start to input energy, can do multiple things beyond just moving faster in its particle level. So it can vibrate, it can rotate, it can do all of these other features. B, on the other hand, has the smaller heat capacity. Okay, and you'll note that we're using a slightly different terminology here. We're not saying specific heat capacity, we're using heat capacity. So heat capacity depends on amount. So the final thing we do with this is we define specific heat capacity under the following terminology. The heat capacity is the slope of this. It's the relationship between temperature change and heat. So we have, let's see if I can find a good spot to put this. Q is equal to the slope, the heat capacity, times delta T, where the greater the slope is, the greater the heat capacity is. So what we can also do is we can say that the heat capacity is equal to the specific heat capacity times the mass, because mass is an integral part of how much energy it's going to take to heat something up. So we can replace this with specific heat capacity by saying mc delta T. Now when I say hc here, this is the heat capacity, the slope of this relationship here. That's equal to the specific heat capacity. So if I had the heat capacity, the slope of that line, I could divide that by the amount of substance and get my specific heat capacity for that substance. So knowing that, when I go back and look at this, this is clearly the slope of energy versus temperature divided by the mass. This is my specific heat capacity. It's telling me how much energy this substance is capable of absorbing per gram per degree Celsius heated. And that should then navigate my calculation method rather than this response here.
Okay, a simple wrong would have done just fine, but